Hello everyone. We are now going to start our AS level physics class uh, on the topic of waves, and this is our waves class lecture number 2. Okay. Today we are going to discuss on the stationary wave formation and about the term resonance. Okay. So first of all, what is resonance? The definition is already given. When a single wave is reflected from a surface, and if the incident and the reflected wave they meet in antiphase, they would form a stationary wave. Okay, and this is what we call the resonance. Okay, for example, look over here, the red wave. Look over here. The red wave is going inside. It is being reflected from this surface and is coming backward. Okay, and they meet in antiphase, producing load. Whatever here is the antinode, this is the node, this is the antinode. Okay, so the ingoing wave and the reflected wave, they have met in antiphase, which is why a stationary wave is formed here, and this incident is what we are calling it as the resonance. Okay. So you must keep in mind that all reflections does not produce resonance. Only resonance of certain frequencies, only resonance of certain frequencies or certain length of the medium can produce resonance. Okay. So now I have mentioned about two things. One is the frequency and one is the length. So the frequency is actually the frequency of the wave which is going and is being reflected, and the length is the length of the medium through which the wave is traveling. Okay, that means for example, in this case, this is the length. Okay, this is the length of the medium. Okay, so only for the certain frequencies and for the certain lengths the resonance is formed. So now look, so different kinds of resonance we are looking at. Okay, you must always remember that if the end that if the end if the end is closed like this end is closed, you must remember that closed end, or at the closed end, we always get nodes. Okay, I'm not writing it full. And at the open end, we always get antinodes. Okay, so at the closed end, we always get nodes, and at the open end, we always get antinodes. Okay. So these are the different kinds of resonance. Look, here is the open end. Okay, here it's the open end. So you have got antinode, node, antinode, node, antinode, node. Okay. Here we have both ends open. So in the both ends we have the antinode. Okay, antinode, 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 da, 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 da. Okay, and if both ends closed, then we have nodes at both ends. So that's so simple. Now, how to find the resonance? Okay, you can find the resonance either by changing the frequency of the wave or by changing the length of the wave. Okay, now what you have to do is that, for example, let me find a space. Okay, here I've got a space. Okay, so you are taking a tube, and here, listen carefully, here you have planned that you will change the length of the medium but not the frequency of the wave. Okay, so what you will do is that first it's like wait, the theme is that for so we are not changing the frequency of the wave, instead we are changing the length of the medium. All right. Okay, now what you will do is that you will first of all you will generate the wave. Please write it down. You will generate the wave, and number 2, you will change the length. You will change the length of the medium until the first resonance is obtained. Okay, until the first resonance is obtained, and in different cases the resonance has got different meanings. Okay, for example, in case of one end open and one end closed, the first resonance looks like this. Okay, the first resonance has minimum number of nodes and antinodes. So here one end open and one end closed. So at the closed end we have node, and the open end we have antinode. And each subsequent and at each subsequent resonance, the number of nodes and number of antinodes will increase by 1 each time. Okay, so tell me how many nodes is here. So we have here one node and one antinode. So this is the first resonance, and in the second resonance we will have 2 nodes and we will have 2 antinodes. Okay, then what about the tube which has both end open? So antinode, antinode, so it will be followed by a node. Okay, so antinode, 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 and a node. Okay, so this is the first resonance in case of both end open. Okay. Okay, so our theme is that generate the wave and then stop at the length at which the first resonance is formed. Okay, now how you will detect the first resonance? Okay, now in case of sound it's quite easier. Okay, for example, let me tell you. For example, you have taken a bullet. You have taken a bullet. Okay, so this is a bullet with a tap around here. Okay, now we have water inside, and here you have a sound generator. Okay, what kind of sound generator is this? Okay, so here you have a sound generator like this. Okay, all right, so sound is being generated from here. So sound wave is coming from here and is being reflected in the upward direction. And what you can do is here you have put your ear. All right, this is your ear, or you can put here a microphone which is connected to cathode ray oscilloscope. All right. Okay, now you will open. So first generate the wave. So sound generator here is turned on. Sound generator is turned on, and sound is being produced from here. Okay, and then we open the tap. Secondly, what we are doing, we are opening the tap. So what's going on is that water level from here is slowly and slowly going down. Okay, because water is coming out of the bottom of the burette. Okay, so water level is going down and down and down, and at a certain level of water, if the initial starting sound was like okay, then at a certain level of water you will hear a sound, or the change will be like okay. So you will hear a loud sound like this. When a loud sound is heard, that means the sound is loud, so the amplitude here must be large. That means obviously here an antinode is formed. Okay, so when you will hear the loudest sound for the first time, that means an antinode is formed at that position. that means a note that means there is a note at the closed end, that means so a resonance or the stationary wave is obtained. Okay. Now if okay, so this is the burette, this is the tap of the burette. Okay. And so for example, this is the water level at which the first resonance is formed. All right. So you may prefer doing it again and like opening the tap again and then carrying on. So water level is going down and down and down, and again after at a certain length you will hear a loud sound. Okay. So that length is called, or that position is called, the second resonance. Okay. So it may be like this. Okay, it may be like this. Now according to the, so here again resonance is formed. So let's look at the variation of frequency. So let's look at the variation of frequency of the intensity of the sound heard against the length. Okay, so when the water level was here, just try to follow. I am trying to illustrate it. Okay, I have to take a large breath. Okay, so this would be the change in the, I know it sounds funny, please don't laugh. So this would be the change in the sound. Okay, so this is how you will find the resonance positions. Okay. Okay, so this is how to find the resonance in all cases. And okay, now in case that you do not want to change the length, instead you want to change the frequency. So firstly, generate the wave. Number two, then carry on changing the frequency of the wave until the first resonance is obtained. Okay. And how we will detect the resonance in case of sound? In case of sound, the resonance will be detected by getting the loudest sound of all. Okay. And okay, so that's number two. And number three, then carry on changing the frequency until more resonance is obtained. Okay. Okay, but here we have a shortcut for the resonance lengths and the resonance frequencies. Okay. Okay, so in case of one end open and one end closed, you will get the frequencies like 2n plus 1 f naught or lengths like 2n plus 1 l naught. This means that suppose you are keeping the frequency constant, you are not changing the frequency, instead you are changing the length of the medium. Okay. So if your first resonance is obtained when the length of the medium is L naught, then second resonance will be obtained when the length is 3L naught. The third resonance is obtained when the length is 5L naught. Okay. So this is how it works. Let me give an example. Suppose this is the length of the medium when the first resonance was obtained, and let the length of the medium is L naught. Okay. So after some more time, you got a second resonance by changing the length of the medium. Okay. So this length has to be 3 times of L naught. Okay. So in case of both end one end open and one end closed, you will get only the odd frequencies of resonance if length is constant, or you will get odd uh, the odd multiples of the resonance length when the frequency is constant. Okay, and in case of both ends same, okay, both ends same means both open or both closed, you will get all possible frequencies or all possible lengths. Okay, so that is the case. Now let's know the use of resonance, that how and where the resonance are used. Okay, so the resonance is basically used in case of finding the wavelength. Okay, to find the resonance, we have to detect the positions of resonance. That means okay, resonance has been obtained. Like in case of sound, when you hear the loudest sound, you can conclude that a resonance has the stationary wave is formed and resonance is obtained. But what will be the case when you cannot hear the wave, like microwave or radio wave? In these cases, what will how you will detect the presence of resonance? Okay, so take a detector that can detect the wave. Okay, for example, for microwave, we use a detector called the probe. Okay, we use a detector called the probe. Now, how to use this probe to find the wavelength of the microwave? Let's see. Okay, so here we have a source that can generate microwave. Okay, and here we have a reflecting medium or a metal plate that can reflect the microwave. Okay, and here we have kept, let me make it more thicker. Okay, and here we have kept the probe. Which is connected to cathode ray oscilloscope. Okay, now what we are doing is that we have turned the microwave source on so that wave is going out from here. Okay, and wave is being reflected from here. Okay, so this is the outgoing wave, this is the outgoing wave, and this is the reflected wave. Okay, so now what we will do is that this is the metal plate reflector. Okay, the CRO will show a reading like this. A wave pattern is obtained on the CRO. So we will move. Secondly, we will move the position of the or we will change the position of this metal plate. We will change the position of this metal plate until the CRO screen shows, actually it shows no reading at all, or just a vertical line like this. This shows that so there is no reading at all. So that means the probe is now sending no signal at all. That means at the position of the probe, we have obtained a node, as we know that at the node the amplitude becomes 0. Okay, so what we have done till now, we have sent just note it down, we have turned on the microwave generator. Okay, and then we have put a probe, this is known as a probe, in between the microwave source and the metal plate reflector. Okay, then what we have done, then we have moved or changed the position of the metal plate reflector until the CRO screen shows no reading or just a horizontal line. So when the CRO screen shows a horizontal line like this, we have fixed the position of the probe at that location, and that location is the node. Okay. Now we have located the node, and okay, so here now here now a scale would be positioned. Okay, a scale would be positioned, and the location of the probe is recorded on the scale. Okay. Now what we will do is that we will move the probe. Okay, what we will do, we will move the probe until again CRO screen shows another horizontal line, again at an adjacent different position. Okay, so that position is called that position would be another node. Let me illustrate this. For example, okay, wait. Okay, so imagine that initially our probe was positioned here. Okay, our probe was positioned here. Okay, so at that moment CRO screen is showing a horizontal line. Now when you are moving the probe slowly towards okay, this position, and then to this position, and then this position, and this position, and then this position. Okay, then what happens is that at this position CRO screen is showing a small reading. At this position CRO screen will show a large reading, because you know that this is the antinode, so a large reading would be obtained. Okay, here CRO screen shows a small reading, here CRO screen shows a further small reading, and here CRO screen shows just a simple horizontal line indicating that there is no reading. That means this is another node. Okay, so now we will measure the distance between these two locations of the probe. Okay, this location is already marked on the scale. Now we will mark this location on the scale and measure the distance between the two locations. Okay, let this distance be d, and you know the distance from one node to another node, or the distance from one antinode to adjacent antinode, is equal to half of a lambda, or half of a wavelength. Okay, so this is one node, this is one node. So from node to node the distance will be half of a wavelength, which is equal to d. All right, so we will write half lambda is equal to d. So lambda will be equal to 2d. All right. Okay, so here we have found the wavelength of the microwave. All right. Okay. Okay, now let's go to finding the wavelength of the sound in the same manner. Okay. Okay, but here we will find, so we can directly detect the length. Okay, so for example, I'm taking a burette. Okay, so this is the length of the okay, let me draw burette several times over here. So this is the burette. Okay, this is the burette, the same burette. Okay, let the first resonance formed when the water level was here, and the second resonance formed when the water level was here. Now let me draw the resonances. Okay, so this is the first resonance. Oops. This is the second resonance. Okay, so yeah, so node to node is half lambda, antinode to antinode is half lambda. So node to antinode will be 1/4 lambda. Okay, now let's move on to calculations. Okay, so this was the position of the first resonance, and this the water level position of the first resonance, this is the water level position of the second resonance. Okay, so here it was a node and here it was a node. So from node to node, let the length is L. Okay, so we can write that half lambda equals to L. So lambda equals to 2L. Okay, you might argue with the fact that we have got resonance. Okay, I'm rubbing this whole thing is. Okay, so you might argue that okay, I know this length from the mouth of the burette to the water level when the first resonance is formed. Okay, if this length is L1, this is a node, this is antinode. So from node to node, the distance will be half lambda. So from node to antinode, the distance will be 1/4 lambda. Okay, so you might prefer saying that okay, so I would like to say that 1/4 lambda equals to L1. Okay, that would be inaccurate to say, because the one thing is that antinode is always formed at a slightly top or at a slightly higher level than the level of the mouth of the tube. Okay, if the mouth of the tube is this, then antinode would be formed slightly above the mouth of the tube. So from the mouth of the tube, from the mouth of the tube to the water level is not exactly the length of the medium. Okay, so that's why it's better that we take two resonances. This is one resonance, this is another resonance, and measure the distance between them. Okay, whatever it is. Okay, so this is the use of resonance to find the wavelength of the sound. Okay, now what we are going to discuss about. Okay, so our next topic we are going to discuss is the Doppler effect. Okay, now what is a Doppler effect? Like okay, let me show you some videos. Okay, so here I'm going to show you that a car is moving with this buzzing its horn, but it's the quality of the sound or the pitch of the sound that you are hearing will be slightly different. Okay, just imagine that you are standing in this position and then trying to listen to the car, to the horn of the car which is coming towards you. Okay, just listen. Okay, have you listened? That it's like the horn has changed, the pitch of the horn has changed. Okay, so why did this happen? Okay, now let's go into the details analysis. Okay, so the thing is that, like suppose you are the source. Suppose you are the observer. Okay, now when the source is this is the source. Okay, so when the source is standing still, so it's emitting waves like this, and the waves are passing through you. Okay, so now what happens when the source is moving towards you? Okay, so this is you are the observer. Now imagine that the source is moving towards you. All right, so now what happens is that when the source is moving towards you, the waves gets closer. Okay, the waves gets closer, so that the wavelength here decreases. All right, the wavelength decreases, and you know V equals to F lambda. So if the wavelength decreases, then the frequency of the wave increases. So that's why you hear it's like that frequency is increasing. Okay, but when the source when the source moves away from the observer, when the source moves away from the observer, it seems that waves are far apart. That means the wavelength increases, and if the wavelength increases, then to keep the velocity same, the frequency of the wave decreases, isn't it? So that's why there is a decrease in frequency, and you listen as if the frequency has decreased. Okay, the pitch has been reduced. It's like okay, it's almost like this. Okay, so now how will we analyze that what is the frequency when the source is moving towards you or the source is going away from you? Okay, so this is the basic formula, that frequency observed divided by frequency emitted is equal to velocity of wave minus velocity of observer, velocity of wave minus velocity of the source. Okay, so this is the basic formula, and since here we have velocities, okay, so velocities has got direction, and the direction that you will always take positive, the positive direction is from the source to the observer. From the source to the observer, the direction has to be taken as positive direction, okay, and all other directions are negative. Okay, so let's see that, for example, this is the source, okay, and this is the observer. Okay, now so this is the source, this is the observer. The source is moving towards you as the v with velocity vs, and observer, and you are also moving towards the source with velocity vo or v naught, and the velocity of the wave is vw, and the actual frequency emitted from the source of the wave emitted from the source is f naught. Okay, or let me tell it like fa. A means actual. Okay, so the positive direction will be from the source to the observer. So here this direction is the positive direction. Okay, so let me tell you the formula. Okay, so from the source to observer, the direction would be positive. All right, so okay, so frequency which is observed divided by frequency emitted from the source or actual is equal to velocity of the wave minus, here it says the velocity of the observer. Now velocity of the okay, so this direction is positive, but observer is moving in that direction, so it has to be a negative velocity. So we put a negative sign before v naught. Okay, but source is moving in that direction, which is the positive direction, so we will put positive with the velocity of the source. Okay, so here it will become plus, and here it stays as minus. Okay, so this is how you will apply the formula of Doppler effect to find the velocity in from different angles and in different cases. Okay, we will have some more detailed discussions of Doppler effect in our worksheets. Okay, so that's all for the Doppler effect.